In the quiet hum of a modern hospital lies one of the most complex machines ever conceived by human engineering, the MRI, or Magnetic Resonance Imaging Scanner. To the casual observer, it is a simple white tube, but inside, it houses a magnetic field 60,000 times stronger than the Earth's own pull. This power is necessary to align the trillions of hydrogen atoms in your body, turning them into tiny radio transmitters. To achieve this, engineers must master the absolute limits of physics, balancing temperatures colder than deep space with electrical currents that would melt standard copper wires. Today, we delve into the engineering marvel of the superconducting magnet and the liquid helium that makes it possible. This is a journey from raw niobium-titanium alloy to the highest resolution images of the human soul. It is a story of extreme cold, incredible pressure, and the mastery of the invisible forces that govern our universe. Prepare to see the world beyond the skin, 1 nanometer at a time. The heart of an MRI isn't just any metal, it is a specialized alloy of niobium and titanium. These two elements are meticulously smelted together, creating a material that, when cooled, allows electricity to flow with zero resistance. If we use standard copper, the heat generated by the massive current would vaporize the machine instantly. Manufacturing these wires is a feat of precision. Thousands of microscopic filaments, each thinner than a human hair, are embedded into a high-purity copper matrix. This composite is then drawn out through industrial dies, stretching the metal into miles of ultrafine wire. These wires must be perfectly uniform, without a single fracture or air bubble. Why? Because at 3 Tesla, even the tiniest imperfection can lead to a catastrophic failure known as a quench. These wires are the veins of the magnet, designed to carry hundreds of amps of current forever, without ever losing a single electron to friction. It is the ultimate expression of material science, turning rare earth metals into the backbone of modern diagnostics. Once the wire is ready, the assembly moves to the winding room, a facility cleaner than a surgical suite. Here, massive robotic spindles begin the agonizingly slow process of winding the solenoid. The wire is laid down layer by layer, often exceeding several miles in total length. Every single millimeter must be positioned with sub-micrometer precision. If the coils are uneven, the magnetic field will be distorted, resulting in blurry, useless images. To counteract the natural fringe of the magnetic field, engineers use a technique called active shielding. This involves winding a second set of coils in the opposite direction on the outside of the main magnet. This second field cancels out the magnetism just outside the machine, preventing the MRI from pulling in metal objects from across the hallway. The tension on these wires is immense. They are wound so tightly that the internal pressures reach hundreds of tons. It is a high-stakes game of geometry and physics, where a single overlapping wire could ruin a multi-million-dollar component. To maintain superconductivity, the magnet must stay at a temperature of 4 degrees Kelvin. That is roughly minus 452 degrees Fahrenheit, just a hair above absolute zero. Keeping it this cold in a room temperature hospital requires a masterpiece of insulation called the cryostat. Think of it as the world's most advanced thermos. The innermost tank contains the liquid helium surrounding the magnet coils. Outside this tank is a vacuum, a literal void designed to prevent any heat from transferring via air molecules. But even a vacuum isn't enough. We add multiple radiation shields, typically made of polished aluminum or silver-plated copper, to reflect thermal radiation back into the environment. Every layer is separated by super insulation, thin sheets of aluminized mylar that look like space blankets. This nested architecture ensures that despite the scorching summer sun outside, the core of the MRI remains one of the coldest places in the known universe. Without this thermal fortress, the liquid helium would boil away in seconds. Liquid helium is a temperamental substance. It is the only element that stays liquid at absolute zero, and it is incredibly rare on Earth. Filling the MRI involves a delicate transfer from massive pressurized dewars. As the liquid enters the cryostat, it hits the warm metal, instantly vaporizing into a thick white fog. Engineers must monitor the pressure constantly. If the pressure builds too fast, the system could explode. Once the magnet is fully submerged, it sits in over 1,500 liters of this precious fluid. In the past, this helium was allowed to slowly boil off, requiring expensive refills every few months. But modern MRI machines use zero boil-off technology. A powerful mechanical refrigerator, known as a cold head, sits atop the machine. It captures the helium gas as it evaporates, compresses it, cools it back into a liquid, and drops it back into the tank. It is a closed-loop system of perpetual cooling, ensuring the magnet stays alive for decades without human intervention. This is how we defy thermodynamics, keeping a sun-strength magnet frozen in time. Now comes the moment of truth, ramping. When the machine is first built, there is no magnetic field. To create it, we must introduce a massive electrical current into the coils. This isn't done with a simple wall plug. Large external power supplies are brought in, injecting hundreds of amperes of current into the superconducting wire. Because there is zero resistance, the current doesn't stop. It builds and builds, creating an immense magnetic pull. Once the desired field strength is reached, usually 1.5 or 3 Tesla, a specialized superconducting switch is closed. This bridges the ends of the coil, creating a continuous loop. At this point, the external power is disconnected. The electricity is now trapped. It flows around the loop forever, without a battery, without a generator. As long as the liquid helium keeps the wire cold, that current will keep moving. This is persistent mode. The magnet is now effectively a permanent electromagnet, a piece of physics that will stay on for as long as the hospital exists. It is a ghost current, haunting the machine with invisible power. A static magnetic field is powerful, but it cannot take a picture. To know where each signal comes from in the body, we need the gradient coils. These are 3 layers of copper ribbons, etched into complex patterns and placed inside the main magnet bore. When current pulses through these coils, they slightly alter the strength of the main magnetic field in specific directions, X, Y, and Z. This creates a magnetic slope. Because the frequency of the hydrogen atoms depends on the magnetic field strength, each tiny slice of your body begins to broadcast at a slightly different radio frequency. The computer can then listen to these frequencies and map them to a specific 3D location. But there's a catch. The massive magnetic field tries to push these gradient coils away, causing them to vibrate violently against their mounts. This vibration is the source of the loud banging or knocking sound you hear during an MRI scan. It is the sound of metal fighting against physics, vibrating at thousands of pounds of force, all to give the computer the coordinates it needs to build a map of your anatomy. The signals emitted by your body are incredibly weak, weaker than a cell phone signal from miles away. To catch them, the MRI must be completely isolated from the outside world. This is achieved by building the entire room inside a Faraday cage. Every wall, the floor, and even the ceiling are lined with continuous sheets of copper or galvanized steel. Even the glass in the observation window contains a fine copper mesh. This cage blocks all external radio interference, from FM radio stations to the spark of a light switch. Inside the machine, specialized radio frequency, or RF coils, act as both the loudspeaker and the microphone. They send a pulse of energy to knock the hydrogen atoms out of alignment, and then they wait. As the atoms realign with the main magnetic field, they release a faint radio echo. The RF coils catch this echo, passing it through a series of ultra-low noise amplifiers. It is a delicate dance of silence, where the smallest bit of electronic noise could look like a tumor or a lesion on the final scan. Precision is everything. Before a patient ever enters, the machine must be shimmed. No matter how perfectly the solenoid was wound, the surrounding environment, the steel beams in the floor, the elevator next door, distorts the magnetic field. For high-quality imaging, the field must be homogeneous, meaning it has the exact same strength everywhere in the center of the bore, down to 1 part per million. Engineers use 2 types of shimming. Passive shimming involves sliding small trays of steel plates into the machine to manually pull the field into shape. Active shimming uses secondary electromagnetic coils to fine-tune the field with electricity. It is a process that can take days. We also perform a stress test. We pulse the gradients at their maximum speed, checking for heat spots or vibrations that could lead to structural fatigue. We test the emergency quench system, a specialized vent that can dump all the liquid helium out of the roof in seconds if the magnet ever overheats. Every bolt, every wire, and every liter of helium is verified, ensuring that this 5-ton beast is as safe as it is powerful. Finally, the engineering culminates in a single moment. A patient lies still. The helium is at 4 Kelvin, the current is flowing, the gradients are pulsing. Within seconds, millions of data points are processed by high-speed computers, using Fourier transforms to turn radio echoes into a visual masterpiece. We see the soft tissues, the flow of blood, the firing of neurons, all with zero ionizing radiation. It is the triumph of the how it's built philosophy. Through the mastery of superconductivity, the extreme management of cryogenics, and the precise control of electromagnetic waves, we have built a window into the living body. A machine that weighs as much as an elephant, is as cold as the void of space, and yet is gentle enough to look at a heartbeat. It is proof that when we push the boundaries of materials and physics, we don't just build tools, we build the future of human health. The MRI, a silent sentry, guarding our lives with the power of the magnet. I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this Tech Archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.